Okay, let's start by covering some of the properties of the atmosphere. So, meteorology is the study of physics, chemistry, and dynamics of the atmosphere. Um, and the atmosphere is the layer of air extending from Earth's surface to a height of a few hundred kilometers. Uh, I had a professor one time compare this. If the Earth was the size of an apple, the atmosphere would be the thickness of the apple's peel. So it's very thin compared to the Earth, and there are four layers: the troposphere, where we live in, the stratosphere, the mesosphere, and the thermosphere. So, I don't know why that skipped. My bad. Okay, so let's start with the troposphere. So you can see this is the bottom part of the atmosphere, it's where we live. However, due to gravity, 90% of the atmosphere's mass is confined within the troposphere. Um, it's where all weather happens. So at the tropopause, the temperature starts warming up, and you can't really get clouds to push past that too far. And it's approximately 12 kilometers deep. Next, we have the stratosphere. This is separated from the troposphere by the tropopause. So the tropopause is this point where the temperature stops decreasing with height and starts increasing again. And the reason why it starts increasing is because of the ozone layer, which absorbs ultraviolet radiation. Then we have the mesosphere, which a lot of electromagnetic phenomena go on. This is where you get aurora borealis and other things. And then you have the thermosphere, where the temperature starts increasing with height again. So the only thing with the thermosphere is that the particles are so far apart that if you went up there, you would freeze to death because you wouldn't get hit with any particles. So the atmosphere is primarily nitrogen, is 78% nitrogen, but there's also 21% oxygen. There's also argon, water vapor, carbon dioxide, ozone, and hydrocarbons. And there's four different things we look at. We look at temperature, pressure, moisture, and wind speed and direction. So, I don't know why it's doing this, sorry. Okay, so let's start with temperature. So, temperature is the measure of the average speed of molecules in the substance. So, the faster the average speed of the molecules, the warmer the substance. And the way that temperature works is when a particle hits something, it generates heat, and the faster it hits that thing, the more heat it generates. So, that's why, like, an ice cube is solid, the particles aren't moving very fast, and so it feels cooler. While if you have, like, steam, it's a gas, and it feels very hot, and that's because the particles are moving fast and they hit you faster. Why does it do this? Sorry. Okay, temperature. Measuring temperature. So we measure temperature with thermometers. So we use Fahrenheit, and the freezing point is 32 degrees Fahrenheit, and the boiling point is 212 degrees Fahrenheit. A lot of places around the world prefer Celsius. The freezing point is 0, and the boiling point is 100. A lot of people are pro Celsius. When I'm not doing math, personally, I'm pro Fahrenheit because it just makes sense that 0 degrees is really cold and 100 degrees is like really warm outside. But scientifically, I would prefer to use Celsius or Kelvin. We usually use Kelvin in our math equations because it just works. So the freezing point of Kelvin is 273 degrees. And this is the freezing point of water, by the way. Different substances have different freezing and boiling points. So the boiling point is 373. and the absolute zero is 0 degrees Kelvin, and that just means that there's no particle motion whatsoever, and it's impossible to achieve in this universe as far as we know, because in order to cool something to 0 degrees Kelvin, you have to have something moving slower than 0 degrees Kelvin to cool it down, so it's just not really possible. There's always just like a little bit of motion. Okay, here are the conversion formulas. I'm not going to ask you to memorize these, but it's like, good to generally know. So like Fahrenheit, it's 9/5 degrees Celsius plus 32. You know, if you want to approximate it really quickly, you can just kind of take this as like multiplying by 2. And then if you want to convert to Celsius, you can subtract 32 and then multiply by 1/2. Like, that's a pretty fast way to do it in your head, but this is more precise. And then Kelvin is from Celsius is pretty easy. You just add 273. So yeah, let's talk about the temperature in the atmospheric layers. We kind of went over this a little bit. So in the troposphere, the Earth is heated from the ground up. So the sun beams come down, and they don't heat the molecules in the atmosphere instantly. They heat the ground, and then the ground radiates upwards. So the temperature is warmest at the ground, and then it cools off. But once it hits the tropopause, which is between the troposphere and the stratosphere, that's when the temperature starts heating back up. So, and that's because of the ozone layer, like I was talking about. It absorbs UV and it lets out heat as energy. So this layer warms up until you hit the stratopause, where you start cooling down again. And then you get to the mesopause, and then you have a lot of radiation coming into the thermosphere and hitting these particles, and it's absorbed as heat, but there's not all that many particles. So even though the temperature of these particles are increasing, there's just not that many particles out there. This is basically outer space, the thermosphere. Pressure. So pressure is just force per unit area. So you can think of it as like the weight of a total column of air on a unit surface. So I like to think about pressure like if you had like the same amount of force in a hammer, and you like pushed a hammer on your hand, versus if you had like a knife and you like pushed a knife through your hand, like one of those is going to go through your skin and the other one it's not. And that's because the area on the knife is smaller. So the same amount of force can do more damage with a smaller unit area. So the atmosphere is pushing down on us at all times, and the average weight per square inch on the Earth's surface is 14.7 pounds per inch. Like, there is an unbelievable amount of weight being pushed on you right now, and you're just like used to it, but it's pretty heavy. So we're using pounds per square inch, but we usually use millibars or pascals. So 1 millibar is equal to 100 pascals. And then the conversion rate for that, 14.7 pounds per inch is 1013.25 millibars, which is equal to 101,325 pascals. So for math equations, we use pascals, but for communicating it to the public or in general, we use millibars. So as you go up in the atmosphere, you have a significant decrease in pressure and density with height, and that's because you have less gravity. Like, the closer you are to Earth's surface, the more pronounced the effect of gravity is, and as you go further away, it's less so. So the particles kind of like center towards the ground. When you get up to 500 millibars, you have half the atmosphere's mass above you and half of it below you. But it's nowhere near like halfway up the atmosphere. It's just halfway up the mass of the atmosphere. So the majority of it's at the ground. And pressure changes very slowly in the horizontal. So if you travel from Oklahoma across the country, the pressure is not going to change all that much. But if you go up, like if you were to hike up a mountain or something, the pressure would change very rapidly. So an example of pressure, so the pressure at Denver versus New York City. So at New York City, you're closer to sea level, so there's more atmosphere above you. And because of that, the pressure is higher. Whereas if you're in Denver, it's a mile high, and so you're not going to have as much atmosphere above you. I used to live in Colorado, and let me tell you, there is not much oxygen out there. Like, it is significantly harder to breathe, and that's just because there is less mass, because gravity is not as prominent. So, the takeaway, the higher the elevation of a particular location, the lower the surface pressure. So, we measure pressure using barometers. An example is a mercury barometer. So, it just like kind of pushes down on it, and however much it's pushing will push the mercury up this tube. And it can vary across the United States widely, mostly because of topography, but also because of like storm systems and whatnot. So mean sea level pressure at a given location, but it's corrected down to sea level, so don't worry about that. Okay, anyway, moisture. Moisture is just the amount of water of like vapor molecules in the air. The amount of water vapor molecules in the air. Yeah. So water vapor, it's an invisible gas composed of individual water vapor molecules. So you don't like see water vapor. Like when you see steam coming off of like a pot or something you're boiling, that's not the gas. It is actually the water condensing as it cools off. So you can't see water vapor. And water vapor is mixed in with other gases. And it's invisible. Yeah. Yeah, so this cloud, this example here, this is not a gas, like these clouds. This is either like liquid water or solid ice crystals. There's other water vapor in the air, but there's just not enough to make a cloud, or it's not cool enough. So moisture, again, vapor pressure. So that's the force per unit area applied only by the water vapor molecules. So basically what you do for this is you just take the percentage that of the atmosphere that is vapor, and you just multiply like the total pressure by that percentage. So like let's say like 2% outside is water vapor, like there's 2% of the molecules are water vapor. Then you just take 2% by times 1013 millibars, and that will give you how much water vapor is in the air. And it changes. And also vapor pressure, it doesn't have to be fully saturated. Like basically you can have like an air mass that isn't fully moist, and that's just the pressure. But whenever you reach the maximum amount of vapor that the atmosphere can hold, that's your saturation vapor pressure. So once you've reached the maximum and your air column is saturated, that's the saturation vapor pressure. The saturation vapor pressure increases with temperature. So like if the temperature outside is like 90 degrees, it's gonna be able to hold a lot more water than if it's like 20 degrees outside. And so that's why relative humidity, like we don't really use that much for science purposes, because like 90% relative humidity when it's 100 degrees outside means something very different than if you're at 90 degrees relative humidity when it's 40 degrees outside. Like, if it's like 90% relative humidity and it's like 115, like, you might like drown. Like, you'll feel like you're drowning. So yeah, it means something very different. So here's the relative humidity. It's the ratio. So it's vapor pressure over saturation vapor pressure. So when the air is saturated, these two things are the same. So relative humidity is 100%. And that just means it's like really wet outside. Like you're in a cloud, basically. You can also reach this 100% relative humidity if you like go and take a shower and you close the door and stuff and your mirror gets all covered with water and steam. Like, that's 100% relative humidity. And that means saturation. Okay, so moisture example 1. So we have all of these cities. So Mesa, Arizona, 25 millibars vapor pressure and 50 millibars saturation vapor pressure. So that means that it is 25 over 50, so that's 50% relative humidity. And then Anchorage, Alaska, it's 6 millibars over 6 millibars, so that's 100%. 20 over 25, so that's 80% relative humidity in Urbana, Illinois. And then 15 over 15 in Worcester, Massachusetts, so that's 100% relative humidity. Which city has the most water vapor in the air? Well, you're going to look at the vapor pressure for this question. So 25 millibars is the highest vapor pressure. So even though these ones have 100% relative humidity, it doesn't matter because there's more water vapor because the vapor pressure is higher in Mesa, Arizona. Which city has the least water vapor? Again, 100% relative humidity, but only 6 millibars of vapor pressure. Highest relative humidity, we are going to say Anchorage and Worcester. They're both at 100% relative humidity. Lowest is Mesa, Arizona, because it's only at 50%. Which city is the warmest? So when you're looking at temperature increases the saturation vapor pressure. So whichever one has the highest saturation vapor pressure is going to be the warmest. So Mesa, Arizona has the highest, and likewise, this coldest city will have the lowest. So Anchorage, Alaska will be the coldest because it has the smallest saturation vapor pressure. Okay, and there is the results that I just calculated in my head. So yeah. Okay, example 2. Assume the vapor pressure remains constant for 24 hours. How does relative humidity change through a 24-hour period? So, if the vapor pressure is the same, if the temperature increases, the saturation vapor pressure is going to go up. And since it's a ratio of vapor pressure over saturation vapor pressure, that means that the relative humidity will go down when the temperature goes up. Likewise, if it cools off, that means that the vapor pressure is the same, but the saturation vapor pressure goes down. So it's vapor pressure for saturation vapor pressure, and so that means it's going to be more moist. So, for instance, if you go outside and it's the early morning and you see dewdrops on the grass, that is because the vapor pressure is high and the saturation vapor pressure is low, so you've reached saturation and that's enough for dew to form. So, yeah, morning cold, saturation vapor pressure is low, relative humidity is high, and in the afternoon, the saturation vapor pressure is high and the relative humidity is low. So, yeah, like I just said. I guess that's the end of the lecture. Okay. Let's go to the next lecture. So we'll talk about global climate and air masses. Oh, we did not talk about that. Okay. My bad. Sorry. This is my first lecture teaching online. Okay. Do we have everything? Let's see. Moisture. That's the end of that. So, okay, I think this is it. Yeah, this is it. Okay, sorry everybody. Okay, so yeah, so that's just a review of everything. So anyway, dew point temperature is the temperature. This is much better calculation than relative humidity. Has mathematical basis and it says something. So dew point temperature is the temperature at which water vapor condenses into liquid water. So it's determined by cooling the air until the water begins to condense. And then the temperature at which this happens is the dew point temperature. So let's say it's 90 degrees outside and the dew point is 74. You feel awful because the dew point is so high. And if the temperature outside were to cool to 74 degrees, the air would become saturated and you would be at 100% relative humidity. So dew point temperature is just the temperature you need to cool the air to form dew, to have saturation. So if the temperature is greater than the dew point, the relative humidity will be less than 100% and you will not have condensation. The air becomes saturated, the temperature is equal to the dew point, and the relative humidity is 100%. And the air cannot hold any more water vapor. Sometimes, though, your air can become super saturated, and that's where your temperature is less than your dew point temperature. And this happens when clouds form. Relative humidity can actually get a little bit above 100%, and that means that water is actively condensing. So what that means is, like, on a microscopic level, if you have air molecules that are evaporating and air molecules that are condensing, if it's subsaturated, it means that more molecules are evaporating than are condensing. If the air molecules are saturated, it means that the same number are evaporating and condensing. And if it's super saturated, it means that more are condensing than are evaporating. So that's like the basic understanding of it on the molecular level. So if you have a higher dew point, that means you have a higher vapor pressure. So dew point, like, the higher the dew point is, the more water you have. And the relative humidity can be qualitatively determined by knowing T and TD. So that means you can't really calculate specific relative humidity with it, but you can say if the dew point temperature is closer to the temperature, you're going to have a higher relative humidity. And but the only way to actually determine relative humidity is by using vapor pressure over saturation vapor pressure. Okay, phase changes. This is fun. So, water is the only atmospheric constituent that exists in all three phases. So, water is amazing. It's awesome. And it uses heat to change states. So, latent heat, it's not temperature change. There's two different types. There's latent, and there is I forgot what it's called right now. We'll get to it. Oh, it's yeah, no, I forgot. Sorry, I took weather and climate like a really long time ago. But I remember it. Latent is statent. So latent heat means you are changing states. And the other type of heat that I forgot, but it's probably in this PowerPoint somewhere, is when you use temperature. So you're changing temperature. But when you're changing states, you're using energy, but you're not changing temperature. So if you have water would prefer to change states than change temperature. it's pretty amazing because you can have water and it will keep something cool or the same temperature instead of heating up because it would rather use that energy to change states. So that's why, like, the ocean, it takes like several months to heat up because the water would just prefer to evaporate than change temperature. So yeah, going from solid to liquid is melting, liquid back to solid is freezing. Going from liquid to gas is vaporization, and gas back to liquid is condensation. Solid to gas is sublimation, and gas to solid is deposition. So, so these top ones here, whenever you want to go to a higher order state, so like the particles are moving really slow, and then over here in gas, they're moving really fast. Heat has to be absorbed. So you're absorbing heat from the outside. And so these are all cooling processes. So like melting, vaporization, or vaporization, sorry. Melting and vaporization and sublimation, heat is absorbed, so they're cooling. And then if you want to condense or freeze something, the particles are moving too fast and it needs to release some heat. So the environment around will heat up as you let go of that energy to move to these lower energy states. Wind. Wind is movement of air. It's created from pressure differentials. So you can think of the atmosphere like a big balloon, and air will travel from higher pressure to lower pressure. And the two important characteristics are direction and speed. So we make those measurements 10 meters above the ground level. I'm assuming that's to get rid of properties of like friction in the ground and stuff. So we have these little pole things. It's called a mesonet tower, and we collect wind data. Why did it do that? Okay. Here's a fun little compass thing. So we report wind direction from where the wind is blowing from. So if you call it a north wind, the wind is blowing from the north to the south. So like northerly, coming from the north, going towards the south. And we use kind of a different angle scale than like regular math. So north is 0 degrees, east is 90 degrees, south is 180, and west is 270. And this is the direction the wind is coming from. So if the wind is coming from 270, it is a westerly wind. And we measure wind speed using an anemometer. It's like this little swirly thing. I messed up, sorry. I keep doing that. So you see up here, we have this little thing that measures wind. We have ones called sonic anemometers that can measure it pretty precisely. And we use units of knots. So 1 knot is equal to 1.15 miles per hour. So you just take, if you want to convert to miles per hour, you just take knots and you multiply it by 1.15. So knots are just slightly faster than miles per hour. Okay, wind barbs. So these are fun. These are kind of like a bow and arrow. They indicate wind speed and direction. So I like to think that this side with like these spikes on them, ticks on them, this is like the bow, like if the little thing at the end. I'm not like really an archery fanatic, but you know what I mean. Like when you pull the bow back, the part that's close to you, and this end is like the arrow that's going in this direction. So these little ticks, these represent the wind speed, and this is the direction it's coming from, where these ticks are, and it's going towards this like little arrow thing. So calm, square, and then if you have 5-knot winds, you'll have this little small tick. It's like a half tick. And then these long ticks are 10 knots. So you add them together. So in this one, you have a long tick and a small tick. So that's 15. 2 long ticks is 20. And then they add these fun little flags. And that's 50 knots. So, and again, you can add. So 65 knots. So 50 for this triangle. The long knot is 10. And the short tick is 5. So you add those together and you get 65. So, yeah, so let's do this example. So this is the direction it's coming from where the ticks are, and it's going towards like the little arrow point. So, never eat shredded wheat. So it's coming from the northwest. So this is northwest. So it's a northwesterly wind. And then to count them, so you have 2 full ticks and a half tick. So 10 knots, 20 knots, 25 knots. So it's read as a northwest wind at 25 knots. Yeah, so it's not too difficult. And you can read these on a map and know really easily where the wind is coming from and what the general wind pattern in the United States looks like, or whatever country you're looking at. Okay, here's an example. This is from the Oklahoma Mesonet, and if you're interested in weather, I highly suggest downloading the Oklahoma Mesonet app. It's free. It has all sorts of stuff to look at. Even it has like a cattle comfort index so you can know how comfortable the cows are out there. So this is like a lot of, so you see these little half ticks right here. So that's 5 knots. Well, they round. So like the 2, it's rounded down. So we'll go to Norman for this day. It's like here, right? Yeah. So it's like around 5 knots. Let's see if we can get anything. So you see these long ones right here. That's 10 knots. This one's 15. Well, rounded up to 15. So you have the long and the half. Yeah. So not too bad. Not too hard to read. And the wind is blowing much different directions, but we can say like up here it's blowing this way. It's a southeasterly wind. In central Oklahoma, it's like a southwesterly wind, so it's blowing like this from the direction it's coming from. And then it gets more southwesterly down in the southern corner, and you even have some westerly wind right here. So this was December 4th, 2019. Who knows what happened on that day? Okay, geography, physics, and chemistry review. Very fun subjects. So, latitude. There are lines that circle the Earth horizontally. My ex-boyfriend always said, latitude is fatitude because it wraps around the Earth like a belt. And I never forgot that, even after I dumped him. So that was amazing. Good on him for teaching me that. I never got it wrong afterwards. So the baseline, the reference latitude, 0 degrees latitude. So 0, the equator. 90 at the poles. So it's positive as you go north, and it's negative as you go south. So North Pole is 90 degrees, and the South Pole is negative 90, and the tropics are around 23.5 north and south. Okay, yeah, so we split it into 3 sections. So the low latitudes, they're the ones closest to the equator, so it's 0 to 30. So we'll start here. So it goes somewhere like through Florida, Panhandle area, Mexico, Louisiana, Arizona, and then southern, it goes through like Chile, I forgot what countries here, but yeah, and then from there to negative 60, you kind of start getting colder, so that extends up through like Canada and further south. And then high latitudes is 60 to 90. And so these, once you get to the high latitudes, that's where the poles start. And it's really cold. So we're at 35.2. So yeah, it seems to check out. We're right about here. So we're not quite in the low latitudes, but we're pretty close. So we're in the lower mid latitudes. Longitude. There are lines that circle the Earth vertically, and honestly, way less scientifically useful than latitude. I'm gonna be honest, we don't really use longitude all that much in meteorology. We mostly just use latitude. But the baseline reference is the prime meridian. I think it runs through Greenwich, England, and it has a longitude of 0 degrees. They're written in east or west degrees, and the minimum is 0, and the maximum is 180 on the other side of the Earth, and then it goes back negative. So our longitude is 97.4 degrees west. And together, the latitude and longitude can describe any location on Earth. U.S. geography. You should know all the states. It's just good practice to know all the states. Some people have a problem with these smaller states. You can remember that Vermont is shaped like a V, and New Hampshire is shaped like an N. New Jersey kind of... I don't know what these look like. Just look at them. Review. States are fun to know. Geography of the United States is important. Yeah. And it's good because if you're forecasting, you kind of need to be able to tell people where the storm is. Okay, physics and chemistry. So we discussed temperature, which is important in physics and chemistry. So energy is a property of a substance that allows for activity. So energy is directly related to temperature. So heat is the energy that is in the process of moving from a warmer to colder substance. So if both substances have the same temperature, that's called thermal equilibrium. So you don't have that energy transference, like warm doesn't go to cold because they're both the same temperature, so they're just in equilibrium. Heat transfer mechanisms. They're physical processes that redistribute energy from regions of higher temperature to regions of lower temperature, which drives the climate and weather. So the Earth and the universe in general hates being out of balance, so it will do anything in its power to restore equilibrium, and that's why we get thunderstorms. They're predominantly created by having two air masses that are at different temperatures run into each other, and the atmosphere wants to reach equilibrium, so it will create a storm. Okay, 3 heat transfer mechanisms. So, radiation. So, this is the transfer of heat from a warmer to a colder substance via electromagnetic waves. Very easy example is the sun. That's the main radiation creator in the world, our world, personally. Probably not in the universe. There's probably much bigger and warmer. Sorry, my cat reaches under my door and hits my door stopper when I kick him out. Sorry. Okay, conduction is the transfer of heat from a warmer to a colder substance via direct contact. So if you touch a stove, that's conduction. You're just touching something hot. So frying an egg on a hot pan or on the sidewalk if you live in Oklahoma in the summer, that's conduction. And then convection is the movement of warmer fluid into a colder fluid. So if you have steam rising from a coffee cup, so you have that that steam coming up and it's mixing with the air around it. Another good example of convection is boiling water or a lava lamp. Convection is predominantly what we are seeing in the atmosphere is convection that creates clouds and storms. Okay, density. Density is equal to mass over volume. And density is the measure of spacing of molecules in some volume of a substance. So the ways to change the density is to change the number of molecules, so change the mass, so increase the mass, to increase the density, or change the volume without changing the number of molecules. So if you decrease the volume and have the same amount of mass, your density will go up. So it's not too difficult of an equation, and if you think about it, it makes a lot of sense. Oh, that's cute. I didn't make these PowerPoints. That's adorable. Okay, so spacing and motion of molecules is different depending on the phase of the substance. Yeah, so like we were talking about earlier. So if you have a gas, like, they're all spread out and stuff, and they're moving fast, and they're not really bonded together. But if they're liquid, they're bonded together, like, a little less closely than if they're solid. But they're still bonded together a little bit. That's why you get, like, cohesion and stuff. But if it's solid, those things are bonded together. Like, it's harder to break a solid than it is to, like, you just run your hand through a gas and, like, it moves the masses apart. Sorry, again, my cat. Okay, so the density of a gas can change quite easily compared to that of a solid. So yeah, you can, like, the density is constantly changing in a gas as molecules run into each other. But if it's solid, they're not really changing that much. The density of an air parcel. Air is a gas, so the molecules move freely, and its density changes easily. Air parcel is a blob of air. I wish my cat would stop hitting my door stopper. The density of an air parcel depends on its temperature. So if you have a warmer air parcel, it's gonna have less density, and if you have a colder parcel, it's going to be more dense, and that's just because of the speed of the molecules. Takeaway, warm air is less dense than cold air. So, this does not mean that warm air is lighter than cold air. It just means that it's the same amount of molecules, but they're more spread out. So, warm air is less dense, so it rises. Cold air is more dense, so it sinks. So, buoyancy is again, my cat, sorry. Buoyancy is the tendency of warm air to rise and cold air to sink. And buoyancy, really, it's just the tendency for things that are less dense to float, but temperature affects buoyancy. And I believe that is the end, so let me make sure there's no more PowerPoints for today. Doesn't look like it, so if y'all have any questions, please feel free to send me an email, and I will see you tomorrow.